All right, the first part of this course, we're going to just talk about the basics in the atmosphere. So might as well start with the gases first. Most of the atmosphere is made up of oxygen and nitrogen. Water vapor is a pretty small, relatively very tiny variable in it, but you can sure see it with the clouds and all of that affect it. So it has a major role in weather, but it's really the other two elements that are the main features, and their proportions don't change. So what I wanted to look at this picture here, if you're at the surface, 22% of the atmosphere at the surface is oxygen. If you're at 300 millibars, 30,000 feet up, 22% of the atmosphere is oxygen. It's just that the pressure is much lower at that altitude compared to down here at the surface, and what happens is the amount of oxygen is less as well. So you have much less air to deal with there. Some of the other things with atmospheric composition here, some of the properties, you're going to talk about the gas law. Well, the gas law relates temperature, density of the air, and pressure. So if you know 2, you always know the third. So when you're looking at a weather map, there's always 2 there. So we'll look at that in a little bit here, but you can actually see pressure basically equals, this is the gas constant, then density, and then temperature. So you always know, if you know one or the other of them, of pressure or temperature, you probably can calculate density from that. So suppose you're flying out in really hot weather out of Phoenix. It's going to make a heck of a difference on the density. If your temperature is really high, then you're probably going to have a lower density. If you look back at the gas law property there, if this is really big, pressure pretty much stays the same. This is where you have to reduce things in density. The opposite holds as well. If you were flying out of Canada or Alaska, then the temperature was really, really cold, but the pressure was still the same, or maybe even a little bit higher. A lot of times higher pressures are up in Canada. The density's got to come up. So you can see how they relate just right there. There are a couple other gases, greenhouse gases, that we're going to talk a lot more about later on here. But just so you'll know what they are, there's carbon dioxide, ozone, methane is another one. There's even particulates that are in the aerosol out there, or aerosols. Some of these might be water droplets, ice crystals, volcanic ash, dust. There's all kind of dust, and there's also sea salt. Each of these can have an effect on an aircraft and on the weather. So this is just a quick introduction to what, just looking at chapter 1 and what you're going to be dealing with in chapter 1. So if you go to the next one here, we'll talk about energy just a minute. There's a driving force for the weather. The driving force is solar radiation. If you didn't have solar radiation, we wouldn't have weather. So we have a driving force of solar radiation. So you got to understand, and we're going to delve a whole lot more into this later on in the next chapters ahead. But remember that the sun comes up in the morning, and it's not directly overhead unless you're somewhere close to the equator, just a little ways above or below it. So if the sun's not directly overhead, you're not getting the full amount of solar radiation available from the sun. But the sun is where we get all of our energy for weather. Every little bit of it comes out of that solar radiation. So remember, time of day has an impact. The maximum amount of solar radiation coming in is probably around noon. However, there's probably still some solar radiation coming in later on in the day. At night, there's a lot of radiation going out from the earth as well. So one of the things they talk about too is how you can relate the temperature to the amount of radiation, or what wavelength of radiation it is actually. And it's the 4th power of temperature. So when it's very, very cold and all, you get a very little bit of much less radiation. But as with the sun, for example, it's really, really hot. You're getting a powerful amount of radiation coming out. So it just shows you the example of how quickly just small temperature changes in temperature can affect the amount of radiation being radiated by some object. And radiation is all in the way of waves. I always like to think of radiation when I'm thinking of waves, wavelengths, as looking at an ocean and you can see the waves going up and down and up and down. Well, as soon as you go up, when one wave's hitting me when I'm at the beach, that's the beginning of a wave. When it goes down to the bottom is the bottom of the wave. And when it comes back up and starts hitting me again at the top of my head, that's the end of the wave. So that's a wavelength. One of the neat things about radiation is that they all move the speed of light. So if I know the wavelength, I immediately know the frequency. So they're very relatable here again. By knowing these things, you can actually relate. And you'll notice that most of our visible spectrum, we have reds, which are the longest waves. And if it gets so ultraviolet, infrared, if you go to infrared, you'd wind up with not being able to see them. And they're even longer wavelengths. And that's what actually radiates from the Earth, because it's, again, the Earth's temperature is much cooler than the sun. Now, if you go to the sun, think of it more and more towards the ultraviolet or the blue end of the spectrum. Now, the sun actually is a maximum right in the visible range where you can see. So you can actually see the radiation coming out from the sun because you're seeing visible light. So we're going to talk a little bit too, just looking at radiation coming in from the sun. You'll see as clouds scatter it back, but clouds also absorb it and they'll reflect it, radiate it back down to the ground. So clouds do two things with the radiation. They can bounce it back, or they can grab it, store it, and send it back towards Earth. About 51% of the radiation reaching from the sun is absorbed by the Earth. Now remember, you got to have an equal balance. So everything, the albedos and all, have got to work out so that you wind up, all the energy that comes in is still going out as well. And that's where the complications all run in. You can see here, some of it's absorbed by the atmosphere, some of it comes in, changes and goes back out from a cloud, and reflects back down to the ground. We have all kind of processes here that are going on, reflecting it back into a cloud, and it comes back down, some of it gets re-radiated. All of these things we're going to talk about in a lot more detail, but this is just an example. And carbon dioxide being a greenhouse gas and methane as being another one, actually absorbs it and then re-emits some of it back to Earth and some of it out into space. So then you have heat transfer. One of the things to think about, we're going to talk about temperature in the next chapter more, but temperatures are basically the amount of kinetic energy in a molecule. Well, heat is the transfer of that kinetic energy from one molecule to another. So conduction, you touch it, you feel it, you can feel the heat, like if you're holding a banister outside your house and it's real hot black banister and the sun's beating on that, it's heating it up. That's conduction, what you feel right there at your hand. Conduction plays a role right at the ground level. But we want to look at more through the vertical level. Convection is another element. Think about convection as like hot air being lifted up. When the air is really, really hot, you ever see a hot air balloon going up or whatever? That's a great way of looking at convection. Advection, another term. Right here you see we have, it's hard to tell, we have all these lines packed together, and they're actual dew points in this case, a measure of moisture. Well, you can see here there's winds, and we're going to talk about winds a lot more here. But they're actually advecting all this moisture northward. So there's a whole bunch of moisture advection. You can get temperature advection as well, radiation this way. So these are just some of the things we're going to be discussing in this module. I wanted to go over a couple things with you. Let's look at a surface weather map. And this is just a basic surface weather map. Well, what you see here is you got a cold front coming into the Midwest. And we're going to talk about what cold fronts are. You're going to do an analysis this week of pressure. Well, I'll try to help you with that in a minute here. But then you can see there's the cold front and stationary front right along the East Coast, warmer air down to the south. And we're going to learn about how to decode all these station symbols here as we go through it. But this is just a sample of what the weather map looks like over the United States right now. If you were to look in the future, here's the forecast for the next 3 days or whatever. And you can see how the fronts are right now. Here's tomorrow. You can see one front's kind of dissipating, but look at the precipitation out in the Midwest. More of it, more thunderstorms out there. By tomorrow evening, yep, still even more. And that front not really moving real fast, is it? But there is a low pressure right there, which here comes the next day. The front's moving a little bit further, finally getting a little closer to West Virginia. So this is just an example of forecasts that are just taking the front's pressure patterns. You can see the high pressure here, low pressure out here. Remember, high pressure, higher pressure. So probably higher density too. Here's just a picture of National Weather Service webpage. Just the current watches and warnings that are out there. All kind of information we could get from this. Just give you an example of satellite pictures right now going on. New GOES 16 is in place, and I happen to like it a lot. But you can really see, this is what they call a geo-color, which is supposed to be a true color. You can actually see thunderstorms down here in the southeastern U.S. down towards Florida. A low spinning around up here, another low out in the Midwest. You can actually see moisture streaming across the Gulf of Mexico into Mexico. Here's your more thunderstorms and all out in the southwest of the U.S. Of course, we have the aviation weather as well. We're going to talk a lot about that as we go on. And let's finish with this, looking at how to analyze pressures. You're going to be dealing with pressures a lot. And one of the things to look at here, the pressure is plotted on the upper right. Here's the station circle, which matches where the station is located. And the upper right is a pressure. Well, if this is below 500, you're probably going to put a 10 in front of it. If it's above 500, you're probably going to put a 9 in front of it. So pretty much everything is, this would be 1011.0 pressure. So there's a lot of it, all very much the same. Here's 1013.0. So say I wanted to draw a 1012 isobar. Here's 1012. Must be a 1012 between these two. So I'm connecting the dots, basically. Going here to here. And we know over here it looks like, well, pressures are a little higher. So maybe 1012 continues up this way. Here it probably goes down. There's 1012. Here's 1040. 1014. So we go down this way. Here's 1012 again, right over in here somewhere. And then down and off the coast. And then back up along the East Coast. So you can see how you just connect the dots of these isobars. And that's what you're going to have to do in some of the exercises I've given you. I tried to give you fairly simple ones to start. But if you have any questions, feel free. Let me help you with them. So hope you got some ideas now, and hope you got an example of what the course is going to be doing. So enjoy this week.